Hello everybody. So let's see. First a quick check. Can you hear me well? Okay, great. So it looks like there is maybe like 10-second delay, but I guess that's what we have to deal with. All right. Welcome to CSCC69. I'm Thierry Sanz, and I'm going to be your instructor. So this summer offering of C69 is going to be quite special for two reasons. One, COVID situation. Okay, so here we have to stay home. That's for the best. So that means that we have to do everything online. We have to do lectures. We have to do office hours, and so on and so forth. Even the exam is going to be actually online. So of course that's not ideal, right? So lectures, for example, there is not like the live kind of back and forth. Here I'm on YouTube. There is a delay. You're asking questions on the chat. That's not ideal. But hopefully we are going to try to do our best to have the lecture as kind of live as possible. So another reason why it's actually a special offering is because it's going to be a new version of the C69 course. So C69 has been offered for a long time at UTSC, but it's the first time I'm teaching it. And it's the occasion for me actually to give it kind of a fresh look. So that's why. So it's going to be a bit experimental sometimes, but hopefully the TA and I are going to be, we're going to work our best to actually provide the best experience as possible. Okay. If you have suggestions about how we can improve, the course, the delivery, and so on, please feel free. Every input that I will get from you is going to be welcome. All right. So before I start, let's see. I'm just gonna look at the chat very quickly, but I guess there will be not questions. Okay, some people say louder. Okay, well, let's see how this improves. All right. So let me first start sharing the screen. All right. So hopefully now you should see the screen. So let's go on full screen. It's going to be even better. So here, what I'm going to try to do is kind of give you a little bit of motivation about why it's important to learn about operating system. So first of all, why do we need operating systems to start with? Well, you all know what's an operating system because you are using one every day, right? The most obvious case is your laptop, the laptop that you are using. Okay, either it's a Mac, a Windows, or Linux. Well, it runs an operating system. Okay, your phone also. Okay, same thing. Whether it's Android, which is actually Linux, or iOS, which is actually like Mac OS a little bit. They are running like two operating systems. But you can think about also data centers. Okay, so here I'm live streaming on YouTube. So YouTube has probably like tons of data center equipment. So all of these data centers run an operating system. Okay, most likely it's gonna be Linux. But think also other stuff, like for example cars or airplane. Okay. Believe it or not, but even a car, a modern car has a lot of computers inside. Okay, I heard a number like even like a regular kind of car has 30 microprocessors. Okay, so imagine now a self-driving car like a Tesla or something like this. It has a lot more computing power, and so it needs some kind of an operating system to run programs. Okay, airplanes as well. Okay, airplane is maybe one of the transportation industry that very early had some kind of computers and automations and so on, and so they have operating systems. Okay, what are those operating systems? Are they different from the computers, for example? Well, for the airplane, yes, but actually Tesla, no, it runs actually on Linux. Even the self-driving features. Other stuff, it's, you know, uh, what we call Internet of Things, you know, the IoTs, all these small devices that we have, okay? Here I have an example of a thermostat, okay, that you have at home, right, to control the temperature. Now it becomes actually more than just controlling temperature. It has all kind of features like voice activated and so on. And so it runs a small operating system. Guess what? Here in this case, it's actually Linux most of the time, okay? So operating systems are everywhere. But again, you know, based on what I told you, you know, it doesn't look like there are many operating systems. Okay, right now, you know, most of the systems we are using are dealing with two. Okay, and I would say even here two families, right? One is like Windows, the other one is Unix based, whether it's actually Linux or macOS. So why do we need to study operating systems? Okay, are you gonna ever build an operating system yourself if there are two that basically we reuse all the time? Well, it is useful. So, okay, maybe a handful of you are really gonna later on work on an operating system adding features. Okay, and when I say a handful, I think it's very optimistic here. But at the same time, you know, you might need to customize an existing operating system for some needs, right? Let me take an example, right? If you work for a small startup, like build an IoT device, well, most likely you're gonna take, for example, Linux, and you're gonna customize it to fit your needs, right? So whatever it is, new hardware, smart devices, self-driving car, data centers, and so on, you might, you know, look at the OS more closely. And so knowing how an operating system works is going to be very useful. The other thing is, actually, an operating system is probably one of the most complex systems that you will ever learn. Okay, and sorry, and so here, just actually learning how an operating system works, even if you know you're not going to build an operating system yourself, it's actually going to give you some concept that later on you can take to build any kind of system. Okay. Also, the other thing is like understand what you use. I mean, at the end of the day, you know, you're going to be a programmer and you're going to build programs are going to be run by the operating system. So how do you make sure that, you know, your program runs efficiently or reliably, okay, or securely, right? So for that, actually, you need to understand how the operating system is going to run your program. Okay, so the more you know about the operating system, the better you're going to be able to actually develop your app. So this is kind of all the reasons, right? So again, you might not design an operating system directly, but understanding how such a complex system is built and basically run all of our program, it's going to be very, very useful. So that's why it's actually a core course here at UTSC. So that's CSCC69 in a nutshell, right? It's an introductory course on operating system design principles. Okay, we are not going to just use an operating system here. We're going to use we're going to look at under the hood how it's built. It's going to be a hands-on experience. Okay, again, you know, just learning from slides or a book, it's not enough. So you will actually build an actual OS. Okay, so here theory and practice goes hand in hand. I know you are hearing that for many courses, but here it's actually true. Stuff that you're going to learn in the lectures, the concept, you're going to directly kind of code them inside the OS, right? So it's going to be very important here. So why do we need a new course? Let me explain first. So the operating system that we use these days, like Linux, Mac, I mean, both of them are Unix based, and Windows, they implement the same kind of concept. Okay, they're not that very different from very high perspective. Actually, those concepts were defined in the 70s. Okay, you were not born, I was not born. And they haven't changed since then. I mean, you can take very old book in operating system, most of the stuff, it's going to be there, it's still going to be true. But there are some new trends, okay? And these new trends actually, although they don't change these fundamental concepts, they actually give a new twist about how to implement operating system. And here I'm going to list only like the three major trends. which are multi-core. Okay, up to maybe like 2010. An operating system runs basically a microprocessor. A microprocessor was single core, and then suddenly, well, first of all, we hit some kind of a physical limit in terms of number of transistors we could put inside a one processor. So suddenly we had this. The manufacturer invented this multi-core thing where actually you put several processors next to each other, okay, and all of them actually running in parallel. Okay, so that actually changed some things. The other thing is like be energy efficient. Okay, in the past, we didn't care about energy efficiency. What we care was performance. Now, these days, because we have mobile phones, because we have IoT devices and so on, most of them run on batteries, well, we care about the energy efficiency. So performance, we want, of course, we want to have great performances, but not at the cost of being energy efficient. Another one is virtualization, cloud computing. Okay, so now we have massive data centers. Sometimes actually we run our programs and so on. We outsource it. We put it inside these data centers. And also these data centers, they're not supercomputers. In the past we had supercomputers, but these days we still have supercomputers, but the trend is not actually to build supercomputers. The trend is actually to take normal kind of processors that we have and then, just scale it and have as many as you can to basically build, data centers and so on, cloud computers. Okay, and so these three major trends have give some kind of a new twist to OSs. Okay, again, the concepts are still the same, but there are some new twists. So that's kind of the motivation for me to create a new course. So and that's something I like to do with all my courses, which is better reflect on the current industry standards and good practices and so on. Try to have a feel about what's going on and where it's going, okay? Although it's hard to predict the future. And also, that's something that I like very much, is to have a very hands-on approach, okay? So, don't get me wrong, the course in the previous offerings, there was a very hands-on approach. But here I'm going to modernize it. And the hands-on approach we're going to do is like we're going to do it on the x86 operating systems. What's x86? Basically, all the computers that we're using every day, and the operating system built on top of that, which is Linux and Windows. So here we are actually going to work with a real OS that can run your computer. Okay, so that's kind of my two goals for revamping this course. So I have to tell you, first of all, it's going to be a tough course. Okay, not because I'm just mean, but because actually operating system at every university, it's always the most challenging course. Okay, when I was a student, the OS course I took was brutal. Okay, so why is it hard? Well, there's a lot of things to read, a lot of materials to digest. Okay, before you're even able to actually produce some code. And that's going to be true again in this course. It's going to be a lot of code. So, halfway implementing a big code, you realize that, oh, wait a second, my design is clunky. And I need to go there and I need to revise my design and so on. So there's a lot of kind of refactoring and so on that you have to do, otherwise you're not going to progress. So for many of you, I think it's going to be one of the most challenging and significant kind of piece of code that you're gonna write, okay? In terms of amount, but also in terms of challenge, in terms of like understanding the concept and so on, okay? So again, I think it's a necessary evil, because at the end you will gain a valuable learning experience, and I hope that after that this course will basically give you some kind of a real experience. It was like this when I was a student. After taking OS, and I took OS at the same time as networking, suddenly, I was not the same. Okay, the way I write code and so on, the way I approach problem was completely different. So hopefully I'm going to give you the same kind of experience. All right. So this is something I'm going to explain right away. What are we going to do in this course, right? Especially because we are in the COVID situation, so most of the weight actually is going to be on the coursework. Okay, so I'm going to talk about that, but first let me make a quick pause just to see if there are questions. Okay, there is a question about the video. So yes, so here we are live, but after that, the video is going to be posted on YouTube, so you can always like watch it later again. Okay, it looks like there are some kind of connection issues, lags, and so on. Okay, again, we're going to try to improve that. So after the lecture, maybe I'm going to send you some kind of a survey and so on to see if, if only a handful of people had lags, or if it's like majority and so on, whether I should change my streaming settings and so on. So we'll see, but I will try to address that. Okay. Okay, so there's some questions about the coursework. So let me right away, I'm not going to answer those questions yet. Let me talk about the coursework. What are you going to work on? I told you you're going to work on a real OS. Okay, you're not going to work directly on Linux and Windows because they are quite complicated. Okay, Windows, first of all, you cannot because it's we don't have access to source code. Linux neither, because it's actually a big code base and it's going to take more than 12 weeks just to get into the understanding how it's implemented. So instead, we're going to use a small operating system that has been developed by Stanford. And they have developed it actually for an educational purpose. Okay, they built it for their operating system class. Since then, many universities have used it, including Caltech, MIT, UCLA, I think, Johns Hopkins, and so on. And that's, I got interested because I saw that all these universities were using that, so it got my interest. The nice thing is like, okay, the code is relatively small, okay, although it's already big. It's written in C, of course. We're doing low-level stuff. But it's built for the x86 hardware, meaning your laptop. Even, I mean, Mac, Windows, whatever. So it means actually you can compile it and you can boot on your real machine and you're going to have an OS. It's not going to be fancy. It's only going to be command line, but it's going to work. So of course, that's not how we're going to work. You're not going to compile and then, reboot your machine and then try to see if it works. It's going to take too much time. So we're not going to do that. Instead, well, we are going to use virtual machines. So let me talk about the project setup here. Unfortunately, we are not going to use the labs. Okay, and I think it's not a good idea. You don't want to work remotely with something where you have to compile and then send over a server and then run and so on. It's going to take too much time. So I think the best is actually you're going to use your laptop. Okay. Hopefully we have a setup here that is going to be easy to do. Okay. So again, you're going to use your laptop. If you cannot use your laptop, it's going to be unfortunately a hard situation. Okay. So let's discuss it offline if you have a problem, but otherwise you're going to use your laptop. Which OS should you have? Linux, Mac, Windows? It doesn't matter. Why? Because we're going to use actually Docker. Okay, what's Docker? Well, you will see, but it's basically some kind of a virtual machines, and inside this, using Docker, actually, we're going to run our OS. Okay, Pintos. Again, actually, if you're really interested about the setup, that's what's going to happen here. We're going to execute programs that are going to run by our OS called Pintos, but this OS is actually going to be run by two x86 emulators, okay, Box and QEMU. These emulators are running on Linux. This Linux is going to run on the Docker container, as I told you, which is actually running on your OS, which is running on your personal computer. Okay, so there are going to be several layers of virtualization in a way. But again, it works actually quite well. Okay, We are still trying to figure out the latest detail. I've asked the TA to actually test it on Mac, Linux, and Windows. So far, they are telling me that yes, it runs smoothly. Okay, even on Windows Edition, a Home Edition, and so on. Okay, so again, we're still trying to tweak some stuff, but we have a setup here that's going to be easy for you to install on your machine and then use locally. Okay, you don't need to have an internet connection, and it's going to be quite fast. So that's what we're going to use. So what are going to be these projects? So in total, there will be 5 projects, 5 assignments. All of them are going to be on the same OS, Pintos. Actually, this OS, I told you, it's there, it's actually working, it exists, but it has some holes, some gaps. Okay, and the goal actually of this assignment is to fill those gaps. So what are the projects? First, there will be a project called bootstrapping. This is actually going to be a very simple project, and I want all of you to do it, so that's why it's going to be individual. What's the goal? Just to get familiar with the setup, look a little bit in the code base. Okay, you're not going to understand everything, but you will have the first kind of ideas, and to do like a small kind of implementation. Okay, so that's why project Zego is going to be quite easy. So all of you will have to do it. But then after that, we're going to have 4 projects. Okay, and all of them are going to be quite challenging. You're going to implement different things here, threads, user space, virtual memory, file system, and so on. I mean, all the kind of the main feature that an operating system has. You can work alone or in team. Okay, and again, I re-insist here, you can work alone. Okay, so let me actually address this question here. Should you work in a team or alone? So here, this is a silly slide where actually there are some just quotes, right? So the first one, alone we can do so little, together we can do so much. This, it implies a little bit that, you know, if you are in a team, you're going to achieve more. Well, I want to take this with a grain of salt. Not necessarily. And I would say here, not at all. Okay. Why? 2 reasons. First of all, don't believe that because you are 2 people working on the same project, you're going to divide the work by 2. No. There's some work that you cannot divide. One is understanding the concept. Both of you, I mean, if you are 2 in the team, the 2 of you have to understand those concepts. Okay. It's not possible that only one understands and the other one does not. So you're going to spend the same amount of time actually reading documentation and then figure things out. The other thing also is like, even if you, after that, once you understand, you split the work, there is some kind of synchronization. There is some kind of, you know, backtracking. You need to wait for the other one and so on. At the end of the day, you know, you don't progress as fast as you would do alone, maybe. Okay, so that's why. I don't think it's going to be a serious advantage to be in a team. But actually, don't get me wrong, working in the team has some advantages. One is actually you can talk, you can look at the same code, you know, you can challenge, the 2 of you can challenge each other to make sure that you have the correct understanding, okay? Stuff that, you know, you cannot do alone. So, again, pros and cons. You decide. The second thing here, coming together is a beginning, keeping together is progress, working together is success. Here I like it because it implies that it's actually hard to work with people, okay? And again, most of the time, you know, you want to work with your friend. Chances are that, you know, you might not be friend at the end of the semester, okay? Because working with people, it's actually hard, okay? So again, that's also another kind of cons of working in teams, right? But if it works well, you know, by all means, it's great. Okay, you will get some gain. And then finally, the last quote: "You rise as a team, you die as a team." Who say that? Well, me. What do I mean by that? You know, if you decide to work as a team, I'm going to treat you as a team, and there will be no individual. Okay, meaning at the end, you know, depending on the result, you might be happy or not. Okay, you might think, okay, well, my teammate didn't put as much work as I did, or my teammate was late, or and so on and so forth. And you know, you might ask me, well, can you look into it? Can you adjust the grades and so on and so forth? I will not do that. Okay, for 2 reasons. One is like I don't have a good way to do that. Okay, I cannot measure the number of lines of code that you implemented, right? Some lines of code are actually takes much time than others. I'm not going to look at the commits on GitHub and so on. That makes no sense. Okay. And the other thing is like, I mean, I'm not going to interfere in the team, right? At the end of the day, it's going to be one voice against the other, and I'm not going to play the referee here. So again, if you decide to work as a team, great. But you will get the result that you have as a team. All right. So what will be the project deliverables and grading? Is it going to be only code? No. So one first thing is like the code that you're going to produce, you're going to be able to test it. We are going to provide automatic tests. And that's the same test actually we're going to use to grade your work. Okay, so you will have a very good idea about how much you will get. Okay, again, if you pass or fail a test, there is no partial credit. We're not going to look at it works almost. But that's a good thing. You have the test. It doesn't mean that you shouldn't do your own test. Okay, of course you should do your own testing, but at least you know what to expect. Another thing will be there is a design document. Why we want you to kind of tell us a little bit how your code is structured and so on. Have some kind of reflection on some questions for each project. So that's going to help us grading. Okay, that's going to help us actually looking at your code. Why? Because we're going to review your code manually. Okay, I'm going to ask the TAs to actually review your code, and we're going to look at all kind of things. Okay, but one is actually going to look at coding style, okay, and the design and so on, right? And they will give you feedback on that. Okay, so it's not only like whether it works or not. It's also about like how you have produced this code. Okay, and so of course you will have this deliverable for each project. Okay. Something that I need to address here. Academic integrity and plagiarism. First of all, why is it important? Well, because actually I'm reusing assignments that has been given to other students in other universities. Okay. You might ask why I'm doing that. Why not coming up with new assignments? Well, okay, I do that for some courses, for sure, but operating system, it's not a good idea. Okay. First of all, the tooling, the code and so on is actually quite complex. And also, you are not going to ask many variations. At the end of the day, an operating system, Windows or Linux, they do very precise stuff. So if I want you kind of to understand this precise concept, this what they do, I'm going to ask you kind of to do the same thing. Okay. So that's why there's not like, I can reinvent kind of like what an operating system do. So that's why, I'm going to give you exercise that other students have done, meaning, well, the solutions might be out there. Okay. Should you use it? Of course not. Okay. So here in this slide, I try to summarize a little bit what you can and can't do, right? So first of all, collaboration is allowed. Okay. Even if you work alone, by the way. Okay. Or even if you work in a group and you want to actually collaborate with another group, you can do it. Now let's be clear about what's collaboration. Okay. Collaboration, well, doesn't mean, hey, here's my code. What do you think? Okay. Collaboration means that you can discuss. You can discuss in terms of concept. You can even discuss in terms of algorithms of testings and so on. What you shouldn't do, of course, is discuss it in terms of specific code. Okay, you're not allowed to discuss a specific code, and you're not even allowed to actually show your code, right? So don't discuss specific implementation detail. Don't look at other people's solutions, even the one online. I know it's very tempting. Don't do it. Okay. And you're not allowed to publish your solution online. Okay, even if you're proud of it after the course, I'm gonna ask you not to do so. Okay, keep it for sure. If an employer, asks you for what's the, maybe best piece of code you have written, you can show this one, right? But don't have it on public GitHub, please. But of course, there is some kind of a gray line in this red line. Okay. Doesn't mean that you cannot Google anything. Well, no, of course you can, right? I mean, when I program, of course I'm looking for code online. Okay, of course I don't remember how to even like iterate through an array or whatever. I'm going to look at code online. So it's fine. You can do that, right? As long as the piece of code that you are looking for is not directly the problem that you're answering. Okay, I know this is vague, but okay, here's an example. You have to implement a process scheduler. Well, don't look for how to implement a process scheduler. And don't copy code that says this is a process scheduler. Okay? If you do that, of course, you understand that you're crossing the line. Okay? Again, here I'm kind of asking for common sense. If you're looking for more like a, kind of a rule, here's my kind of rule of thumb. More than 5 lines of code, it's okay. Okay? But what I want you to do is actually put the source of the URL in the comment. You know, you copy paste, of course you're going to customize, but just put the link as a comment in your C code. More than 25 lines, don't do it. Okay, I would prefer that you really understand, you customize it, because if I see code there that is not relevant and so on, it's going to raise some concerns. So that's why 125 lines, don't do that. Okay, again, there's no like absolute truth here. It's going to be a lot of common sense, but please, don't take shortcuts. I mean, there is one obvious advantage why you shouldn't do it, right? One is learning. There is a learning outcome. If you copy code, you're not going to learn it, right? And by the way, if you don't learn it, you're not going to do well in the exam, okay? Which has some weight still. And in case you're doing it, first of all, I can catch you easily. The code is big enough so that similarities are going to be evident, okay? I'm going to use automatic tools to find them, and if I found those evidences, you're going to be forwarded to Dean's office. Okay, each project is big enough so that I'm not going to even bother giving you a 0. I'm going to forward it to Dean's office that will make a decision. So please don't do it. Okay. Again, if you have some doubts, if you have some concern or whatever, please talk to me before submitting anything. That's not your own. All right. Let me continue a little bit. But again, I understand that this is stressful. Okay, it's stressful times, first of all, and it might be a stressful course because there's a lot of things to do. So I don't do that usually, but here I'm going to experiment with something which is a late policy. So each team, okay, not individual teams, will have 4 days grace period, okay, that you can use over the semester. Okay. So these late days, you can use them all at once. Project 1, for example, you use 4 days. It means that you will not have any late days left for the other project. Okay, or you can use 1 for project 1, and then maybe 3 for project 4. Okay, so you do whatever you want. The days are indivisible, right? Even if you take like a morning, okay, it's going to be 1 day. What can you use this day for? Because sometimes stuff happen, okay, and stuff happens sometimes at the last minute, okay, but it can so I understand that, and I don't want you to kind of like get a bad mark on a project because of that. Also because you might have other stuff like interviews, conferences, although I mean in this situation I doubt you're going to attend conference really, but you need to run some errands, whatever, okay, so use those days, but use them wisely, okay. If you use them because you have procrastinated, it's not gonna do well. Okay, so use them only. You can use them for project 1 to 4, not for project 0. Okay. All right. So that's about kind of the coursework. I'm going to talk about it again when we look at the syllabus, but that was an important part. So let's see. Is there any questions? Oh yeah, if you have a x64. So the question is, if you have an x64, which most of us have, by the way, it means 64-bit architecture. Are we going to be able to do assignments? The answer is yes, no problem. Can I speak louder? I would try. I'm already I feel I'm yelling. I think it's my microphone settings. So that's something for sure I'm going to try to fix. Do you still write a bunch of assembly? I'm going to talk about that a little bit, but no, it's going to be mainly in C. Why 2 emulators? Oh, good questions. Well, actually, you're going to discover that in the project 0, why we're using 2 emulators. Will the setup work on WSL2? I'm not sure what it means. It's Windows something. Okay, I'm not sure what it is, but if it's Windows, hopefully, yes. Oh, how many in the team? Yes. One, I mean, you can be a team of 1 or 3. Not more. Don't ask me for 4. I think 3 is already too much, too many. 3, there's always one that doesn't do much. 4, you're running into problems such as team dynamics, team organizations, and so on. You know, all the stuff that you're doing in CO1. I don't want you to get into that. Okay, I just want you to be, you know, efficient and right away produce some code. So that's why 3, it's actually already it's the maximum. Can we have it on GitHub and keep it private? Oh yeah, after the course, of course. Yeah, you can have it on your GitHub, and as long as you keep it private, that's fine. Is it 4 business days? Well, yes, in a way, because all the assignments are going to be due on Sunday. So yes, it's going to be like, you know, you can take up to Thursday if you take all of your 4 days. Oh, sorry, again about the volume. Okay, I will try to fix it. Let's see if I can fix it directly from here. Okay, let's see. I've reduced my volume here. Let's see if it's better. Okay, if it's worse, let me know. If it's better, fine. Oh, sorry, 300% and the sound is good at that point. Okay. Sorry. I will try to fix that. Let's see if the tweak I've done works. All right. So let's look quickly at the syllabus, which is actually on the course webpage. So I'm going to minimize that. All right. So everything is on the course webpage, hopefully. So you can use that. Let's go quickly on the kind of intro. Prerequisite. Yes, there are 3 prerequisite in the. Okay, it's worse. Okay, let me try to fix it. If I go in the settings. Okay, is that better now? Okay, let's see. Yeah, I went back to original and I even tweaked it something else. Okay, hopefully it works. Let's see. I'm just going to keep talking. I'm going to keep this window open here to see. Oh, better. Yes. Okay, good. All right. Okay. Sorry if I mistreat your ears. All right. So I was saying basically, let's look at the syllabus. Everything is online, hopefully. So let's look quickly at the first page. Prerequisite. Hopefully all of you have the 3 prerequisites, which is B58, B09, and B07. They are mandatory. I cannot go without them, okay? You need to know about hardware stuff from B58. You need to know about system programming from B09, okay? And you need to have some kind of experience working with, you know, kind of significant piece of software, that's B07, okay? So I cannot compromise with that, so you're going to be kicked out if you don't have this prereq. Okay. So core staff. So I'm not alone. I have 4 great TAs. I mean, people got A+ in this course, and people that I believe they're actually hackers, and they're going to help me actually make sure that this course is as smooth as possible. Okay. And I'm sure that they're going to help you getting the result that you want. Okay, so I'm glad to have them, and we're going to work out in this course. Course timing. Okay, so we have 2 lecture sections, but it doesn't matter because it's on the same day. Anyway, it's going to be online. There are tutorials. What are we going to do in tutorials? Actually, I will tell you. I'm not sure yet. Okay, for sure the tutorial is going to be like some kind of a big help session with the TA. Maybe some weeks I'm gonna ask the TA to do some presentation to show you some examples and so on. Sometimes it's just gonna be, the TA standing there and saying, do you have questions? Okay. It's gonna be online, of course. We're gonna use the Kirkus stuff. I haven't opened Kirkus yet, but we're gonna use that. It works well apparently. About the course website. So you have this website, and this website is actually, you can have the source code. It's on GitHub. There might be some stuff on the GitHub that is not on the course website, like snippets of code, the keynote slides, for example, if you're on Mac and you want to look at the keynote slides. So there are more stuff on the GitHub. It's good to take a look once in a while. Piazza. I'm going to use Piazza a lot, and please, let's use Piazza for everything. Even if you have to ask me some kind of a very personal questions about the course, right? Use Piazza. Why? Because I have too many emails, and sometimes I'm not very good with managing emails and so on, and I like to have all my CSCC69 stuff on Piazza. And I'm going to check regularly, okay? Sometimes I check more Piazza actually than emails. I have an anonymous feedback form. If you need, if you feel that you need to be anonymous, you want to tell me something, okay, well, use it. You be anonymous for me, maybe not for Google, but you be anonymous. Okay, what's the marking scheme? So again, it's a very heavy hands-on course. So of course, there's a lot of weight on the projects. But also we are in some kind of we are in a COVID situation and so on. There will not be an in-person final exam, so it's going to be a take-home exam. So I cannot have this exam weight too much. But at the same time, I want it to be worth something. Okay, I think it's good to have a final exam, even if it's take-home exam. I want to have some kind of a brief review about what you have seen in the course. Okay, so even if I know it's going to be open book and so on. But I want you to have this kind of quick review. So there will be a final exam, 20%. Submission policy, okay. In a nutshell, you're going to submit stuff on GitHub. It has to work. It has to compile. If it doesn't, well, it doesn't. Okay, and you might get a 0 for the assignment. We are not going to, we're not going to modify it just to test the stuff. Okay. It says no late submission. This is something I haven't updated yet, but I will update it later with the late policy I just told you, right? The 4 grace days. Remark policy, we're going to try to give you feedback as soon as we can, although it's going to take time for us to grade the project. And as soon as the grades are out, I'm going to ask you, please look at it, and no more than 1 week for a remark request, okay? After 1 week, I want all of this to get behind and concentrate on the newer stuff. Academic integrity, I already talked about that. This is some blurb, formalizing what I just said. But again, it's really important. Okay, it's important for you to learn, and it's important to, just to make sure that you're not cutting corners. Okay, so we want to be ethical here. Accessibility. If you have some needs, I don't know how they're going to be addressed in this situation when we are working from home, but let me know. Okay, if we can do something with the accessibility office, we will. And then here's some acknowledgements, okay, because I told you, right, I looked at how other universities have done their work. I've asked for to reuse their materials. I've asked them for collaborations and so on, and actually 2 of them actually have agreed, so Stanford and John Hopkins. So I might reuse some of their material there, okay, although I like to give it my twist every time. And also Ben Pfaff is actually the creator of Pintos, and he gave me the authorization to use it for the course, and he gave me access also to all kind of stuff that I cannot share with you because they are kind of like design documents and so on and so forth. Okay, so so that's great. Other stuff. So the project. So project is going to be here. It's actually. So I'm going to say everything is there, almost. Actually, project 0. Which is the first one, it's not ready yet. I've asked the TA to look into it. We're going to make some small, make sure that everything runs well. So maybe I'm going to ask you, don't look at it yet, or at least don't start coding, because we're going to change a little bit the handout. Okay. Otherwise, the others, they are already there. there is tons of stuff. Okay, so here basically, I mean, you can go into like the big reference guide. Everything is there, from the project to explaining how Pintos work and so on and so forth. It's a lot of documentation, but you will have to go through that. Okay, so I told you there's kind of a big kind of self-learning part, and it's all there. I think the documentation is great. It's very exhaustive, so I'm sure this is going to be a great help. You're going to have it in HTML or in PDF, and so on and so forth. Most of the time you have to read, reread, and so on, digest before you are able to produce some code. Okay, so this is going to be your best friend here. All right, other stuff, okay, debugging tools and so on. We are trying to figure it out. I'm going to put like quick updates on that soon. Okay, so I'm saying don't start writing code for Project Zero, but please look into the documentation today. Okay, I told you Project Zero is going to be individual. All of you have to do it, just because I want all of you to actually get the kind of like the bootstrapping part. And then after that, it's group if you want. Okay, you can work alone if you want. Okay, again, the advantage of working in a team is not that great. Okay, so feel free to do it the way you want. If you decide to work as a team for Project One, I'm going to assume you're going to stay with the same team until the end, right? Okay. Some resources can be useful. So first of all, one resource, a textbook. It's free. I mean, this textbook is online. Okay, so and it's a good textbook, and I'm going to try actually to keep track of every week which chapter is relevant for the current materials. Okay, so do it. Okay. Okay. Other books that actually I'm using. I'm looking at these books as I prepare for the course. So these ones are not online, but you know, if you find them, could be good as well. Other stuff about like Git, if you're not familiar with Git, but I guess you have used it in BO7 or CO1 and so on. Otherwise, well, look into it and ask the TA for help right away, and it's going to teach you a little bit about Git. But otherwise, here you have two kind of good stuff. Some stuff about C, x86 assembly and Unix programming. I doubt you need, I mean, most of the stuff that you need, you have seen them in BO9 and B58. Okay. But you know, if you need some kind of refresher, everything is there. If you want to learn more about OSs in general, there is an OS Dev Wiki, which is great. Great resources for everybody building OSs. And then some kind of documentation about the Intel and AMD, right? The processors, because those OS are built for a microprocessor. So here it explains kind of the differences between the two. Okay. Other stuff, Piazza, the GitHub for this website, okay, and the feedback form is here. Okay. So let's see. Let me turn here to see if we have any questions. Okay, can we please get a video for the wall setup? Yeah. So that's something I'm gonna do. I'm waiting for the TA they're testing it right now as we speak on Windows and so on. They're finalizing some stuff. After that, I will either kind of like send you some clear instructions about how to install it. I might do a video, that's actually a good idea. And in worst case scenario, you're gonna have a help session with the TAs during the office hours. Starting maybe next week, right? So again, that's not going to slow you down, okay? Even before you are able to actually produce some code, you have to do all the readings and so on. So that you can start. Can we work in a team for some assignments and solo for the others? No. So decide that. You have basically like 2 or 3 weeks to decide before Project One starts. 2 weeks actually. So decide that before. Recorded? Probably not. Okay. And what's going to happen during the tutorial? Well, we'll see. Okay. It depends on the needs and so on. We might adjust things. You can switch teams members and so on. No. Okay. Choose wisely who you're working with.
but after that, no. And if your teammate dropped the course, well, you're alone basically. Okay, so again, people struggling running box on Pintos. Yes, that's actually something the TAs are looking right now with box. Hopefully, we're going to figure this out very quickly. Okay, so tweaking that we need to have. So box doesn't work, Kimu works though. Yeah, again, the book there, it's actually, it's a good, it's very good reference. So yeah, you should read it. Okay, and somebody's confused about what exactly? If it's about the reading, then okay. If you are confused, then do the readings. Okay. I'm going to cover the same concept, right? But maybe the book is going to go into more detail sometimes. And it's always good to have kind of two different ways to approach the same concept. So yes, do it. Okay. Some streaming delays and so on. If some of you are like streamers or YouTube experts and so on, again, if you have suggestions to give me, feel free. Okay, I've tried to tweak already my settings and so on, but yeah. Okay. Oh, wait a second. It looks like okay, it looks like I have a low quality here. What's going on? Okay, so it looks like it's lagging actually. I'm not sure if I can do something without closing the stream. So let's see. Ah, okay, the connection is back. Okay, hopefully it works. All right. So let me go back to the slides quickly. So, I mean, I'm just going to finish the slides like this. So, how to succeed in the course? Well, you have to stay afloat with the materials and the readings. Okay, we're going to pile up concept week after week. The one depending on the previous one and so on. Even the assignments are going to be like this, by the way. They're cumulative by nature. So you have to stay afloat, right? So that's something you have to do. And then start working project from day one, okay? Okay, I know every courses they say that, okay? But here, this is, I mean, if there is one course where it's true, it's really this one, okay? If you start at the last minute, you will not have time to digest the materials. You will not have time to refactor your code if needed. You will not have all of this precious time, right? If you start in the last few days, even if you start the last week of the assignment is due, you're going to be in serious trouble, okay? You're going to be in panic mode. You're going to ask questions that can be easily answered by reading the materials. So that's not going to be a good experience, okay? So please start working on the project early. So yeah, and then some acknowledgements. Yes, Ryan Huang here from Johns Hopkins. I borrowed Project Zero from him. I look at his slides that are actually quite good. So yeah, I really want to thank him for that. Ben Pfaff and David Mazier, who kind of allow me to use Pintos for the course. So that's actually also great. All right. So I'm done with the first part. The second part. But again, maybe I'm going to do a small pause for to see if there are some questions about the logistics and so on. So here we're going to start kind of talking about OSs. Yeah, somebody say I should stream in 720p with a good bitrate. Yeah, this is maybe something I need to tweak for sure. Am I using actually wireless? But I don't think it's the bottleneck. I'm not sure. Okay. So let's see, let's continue. Hopefully this is something also I'm gonna try to improve next. Okay. Okay, let me continue and we'll see. Hopefully the connection is gonna be get better. All right, so what I'm gonna try to do here is to give you some kind of a big picture of the entire course. Okay, so I'm not going to start talking right away about the details, but I'm really going to try to paint some kind of a big picture. So here, what I'm going to do in this lecture is, first of all, I'm going to try to define what an operating system is, okay, to have a better understanding about what we are dealing here. Also, I will also explain how actually an OS works in a nutshell. Okay? And of course, throughout the semester, we're going to go into more details. But also, I'm going to try here to bridge the gap really with what you know. And you know two things, right? You know about hardware, and you have done some hardware programming and so on in B58. On the other hand, you have done some system programming in B09, right? You have programmed with processes, multiprocess, forks, you have programmed with sockets, and so on and so forth. So you have done some system programming there. The OS actually sits kind of in the middle, right? So here, I'm going to try to kind of join B58 and B09, and that's going to be kind of this course. Also, what I'm going to try to do is to give you an overview of the course content and the project at the same time. Okay. So here, if I were to divide this big picture into 5 pieces, it would be the same pieces actually I'm going to divide the assignments. Okay. So first, it's like we need something called bootstrapping and system calls. Okay. How does an OS start? Because understanding how an OS starts actually already tells a lot about what an OS is supposed to do. And then we're going to try to define the notion of system calls, okay, that are essential for operating systems. We're going to talk about concurrency. So we're going to see why we need concurrency to start with. And then we're going to try to okay, so I'm going to stop here because it looks like there is a problem with the connection. All right. Okay. Okay, so let's see. Okay, let me try to fix the connection here because it doesn't work. Okay, it looks like the connection is back. It's kind of annoying. Okay, let me resume here then. It looks like it's fine now. All right, so let's start again full screen. All right, so I was saying basically that, here I'm going to talk about like 5 pieces, and actually these 5 pieces correspond to the project. Okay, so let's look at piece number 1. So here, what I'm going to start with is what you know from B58. So, and even I'm going to simplify it a lot. Okay, so in B58, what you saw is what's a computing architecture. Okay, and basically, in a nutshell, it's memory and a CPU. Okay, when I say memory here, what I mean by that is you have kind of devices. Okay, whether it's RAM or it's the keyboard or it's a screen or anything like even like an actuator, controller, and so on and so forth. Right. So what you have seen is actually the CPU. What it does, it does operations in memory. Okay, and it has memory address and tries to read and write bits there. And whether behind that memory address there is like a RAM where it's actually going to store data, or there is a device that is going to do something, it's kind of the same. So that's the very simple kind of view, right? So I have the memory on the side. The memory, again, it's not only the RAM. I'm going to divide it into 3 pieces. There's all the kind of like addresses that are about the input-output, the devices. There's of course the RAM, which is a big chunk of this memory, and there's a small kind of area which is the boot. Okay. All right. So first, let's talk about processor. When we talk about the processor, so here we talk on our laptop. Usually we talk about Intel or AMD. On the mobile phone, we talk about ARM. So there are different kind of processors. Each processors have something we call an instruction set. What are that? Well, basically, operations that you can actually write in assembly code. So a processor executes instructions stored in memory, and each instruction is basically just a bit string. Okay, the processor only see bits, right? And this bit string, when the processor executes it, it performs something. Whether it's an operation, a mathematical operation, either it's like reading and writing in memory, whether it's actually the RAM or devices. It's doing some bit logic, okay, sometimes shifting bits and so on, rotating, stuff like that, or doing some jumps. Okay, so it executes instructions and then it's going to jump at other places in memory. Okay, so how many instructions are inside each processor? Well, it depends, it varies. Okay, but roughly right now in the modern processors we have 2,000 instructions on x86. Okay, 64-bit architecture. So that's a lot of instructions. Again, most of the time we don't use our instruction ourselves as a developer, right? As a developer, we have higher languages. Usually we don't write in assembly code, but we compile into this assembly. So what you have seen also in B58 is, well, how to run a program, basically, okay? And here, okay, some people have okay. I don't know if you can hear me, but let's see. I'm just trying to change some settings to see if I can improve the. Okay. Okay. All right, let's see. Okay. So, we're back. Hopefully you can hear me. Okay. I hope the connection is going to be more stable now. All right. So, let's move that to full screen. Okay, so let me start again. So here, yes, let's start again with these slides. So the processors have different kind of instructions. So a program working on Intel is not going to be the same program as working on AMD. So let's see. Okay, no. So can you hear me well? Yeah, maybe we're going to switch to BB Collaborate. I think this is not working. It works well the last semester. I don't know what's going on this semester. Okay, anyway. So here's what I'm going to do. It looks like many people have issues, so I'm going to try to finish this lecture, and then I will see what's recorded by YouTube. After that, we'll see. I'm going to send you a survey to see if we should continue with this YouTube or not. Otherwise, we'll switch to something else. Okay. All right. So let's move on. So I was saying. All right. So what actually the processor executes, it executes instructions, and these instructions have. Each processor has specific instructions, right? And it's not going to be the same between Intel, AMD, and ARM, for example, which is on mobile phones. So each instruction, it's just a bit string because the processor only sees actually bit string, and he understands this bit string as an operation. Either it's doing some kind of mathematical operation, a read-write in memory, whether it's I/O devices or RAM. It's doing some logic and it's doing some jumps. Jump to actually switch the execution. Okay. So for example, on modern processors, there are roughly 2,000 instructions. Okay. But again, we don't program directly in assembly usually, right? What we program is in C, and then we compile it for this specific processor. Okay. So in B58, you have done that. You have done a little bit of assembly actually, and you run your program. So when you run your program, what's going on? Well, you have roughly 2 pointers. One is the instruction pointer, it's what the CPU is executing. And the other one, which we call stack pointer, is used actually to... So something to understand is data and instructions, they're all in memory. They're all in the same space, kind of. And they're not different from another, right? It's only if the CPU is going to understand it as an instruction or as data. Okay, so it depends on the pointers. So here, there's another pointer I'm not talking about, right? There's a EBP, there's a frame pointer, the base pointer, but I'm going to simplify it here. So you run your code and then you can store data. If you have done some kind of, if you have written even in assembly functions, or if you have allocated some buffers and so on, you know that you're playing with two things, the stack and the heap. Okay. So here, I'm not going to go into detail, but basically, we are storing stuff in memory, and this stuff are needed to run the program. Okay. So we don't need much detail about that, but that's basically running one program, and that's what you have done in B58. But first, let's start with the first concept here, which is bootstrapping and system calls. So the problem that we are trying to solve here is the following. When you boot your computer, what is inside memory? I mean, what's the CPU actually executes? It's empty. And the RAM, there's no information in the RAM. Usually the RAM is volatile, meaning when it's the computer is off, there is no data there. Okay. So what happened when you power on the computer? What you have done in B58 was a little bit different. You didn't have one system alone, right? You had two computers, and you were using kind of like a normal computer to actually compile the code and then push it to the small kind of test platform that you had, right? But the computer is different, right? I mean, when you power on, there is no other computers basically to tell the system what to do. So we need to bootstrap it, okay? So what's happening when you bootstrap it? Well, by default, the CPU starts executing code contained in the boot section of the memory. And this boot section has something we call the BIOS, okay? What's a BIOS? It's a program, okay? It's a basic input-output system. And that's the first thing it's going to execute when it starts, okay? So this BIOS is usually in a chipset. That's why here I have this small chipset here, but it's just like a piece of memory. What this BIOS does, it actually it loads the bootloader. From where? From a device. And here, most of the time on your computer, it's actually the hard drive, but you can boot on the USB stick if you want, or USB drive. You can also boot on the network. Okay, you can actually grab the operating system, the bootloader from the network, right? It depends on the configuration, because actually you can configure the BIOS to change that, okay? By default, we boot on the hard drive. So once the bootloader is loaded, and it's loaded again in this kind of boot section, this bootloader, it's kind of like a small program that will actually start the operating system, that will load the operating system. And the thing that we load is called the kernel, okay, the OS kernel in general. And this time it's going to be loaded in the RAM, okay, so not in the boot section anymore. And then it's gonna be there, and it's gonna be kind of the first process to be executed. Okay, the bootloader now is actually shutting down. So once the kernel starts, the first thing it does is so it's gonna do a bunch of things, and then it's gonna start some kind of a user interface. Okay, so it can be the fancy graphics user interface and so on, but the minimal thing is actually some kind of a terminal, okay, that you can enter commands. So here let's take the example of a bash terminal. Okay, you start a Linux server, for example, and you have a terminal there. And then from this terminal, then the user can interact with the OS, and what the users can do is actually execute programs. Okay, and so you can start a program from command line. Once it's finished, you can actually repeat, start another command, and so on and so forth. Okay, so you can do that. And all of these programs actually are going to be loaded, of course, in the RAM, and they're going to be executed. And the processor is going to actually, put stuff on the stack and the heap and so on. Okay. So if you look at that, you might think, okay, well, there is always one program at a time that is executed, right? So it's not really that different than what we had before. Okay. Well, we'll see. But imagine writing a program for like that, right? So imagine, for example, in your B58 class, you have to write the program bash, which is write the terminal. How do you do that? So first of all, you need to, for example, read some keyboard's input from the user. Okay, so you know how to do IO devices, how to interact with IO device, and you know that what you have to do is like you need to know where the keyboard is connected, and then you have to write into a buffer to kind of ask for some data. When the data is ready, there is another buffer, another memory address that tells you, yes, there is something, and then you read from there, right? You have done that in B58. So you can write this program yourself, but wait a second, which device are you going to read from, right? So if you try to write a program that is going to work in every machine, right? How do you know where the keyboard is exactly, okay? Is it on the PS2 port? Is it a USB keyboard? Is it a Bluetooth keyboard? Or is it even like somebody connected remotely on the network? Okay, so here, this is all to tell you that usually you don't do that. When you write a user program, you don't interact directly with the device. what you do is you're going to use some kind of a function that says, please read input from the keyboard, whatever that is, right? So that's going to be the first thing that the OS is going to do. It's going to abstract some functionalities that for you to actually write a program. And usually when you write a program in C and so on, okay, or even lower than that, even if you write in assembly, okay, you don't deal directly with I/O interaction, right? So what the OS is going to do is going to provide something we call a system call. What's a system call? You can think about it as a big API. Okay, it's an API for everything that the operating system and the hardware have to offer. Okay, so it's a big API for the programmer, and there are 5 categories of system calls. Okay, so one is process control. We're going to see that actually, how to kind of basically start and stop processes, and here you should understand programs basically. File management, how to basically read and write files, how to structure the files into directories, and so on and so forth. Device management, so basically input output. Okay, so it's going to provide you access to that. Information maintenance as well, configuring the system, simple stuff like the date of the system, the time, and so on. Communication between programs, how they will exchange data and so on. And some protection. Okay, protection, we will see that because at some point you want a program running with some kind of privileges, not the full privilege. Okay, how many system calls are there? Well, for example, if you take Linux, there are roughly 400 system calls. Okay, so you might believe it's big. It's actually not many, right? So imagine a library with 400 functions. Okay, at the end of the day, it's not kind of too large. If you're wondering about Windows, I think Windows has around 700 or 800. Okay, I haven't looked at the latest number, but that's the number of system calls it has. There's even a cheat sheet here if you want to look at all these system calls. So when you write a program, in C, you might actually look at, call these system calls. In reality, not really. Okay. In reality, there's a lot more abstractions than that. Okay, and here, if I look at on the side at this big stack here, this is what kind of close to the reality about what's happening. Imagine you want to write a shell. Okay, you want to write a bash shell. Well, you're not going to directly do a system call. You're going to write something. You're going to call something which you call the C standard library, for example. Okay, and you do that in C, right? When you need to actually read a keyboard input, you do scanf. And then this C standard library might call again another system library, right? This system library will do the system call, okay? But even that system call, because it has to interact with the keyboard, with the I/O device, it's not going to do it directly. It's going to go through a kernel modules that will have some kind of an interface, and this interface is going to talk to a driver, okay? A device driver that usually is provided by the manufacturer of the keyboard. Okay, so you see here, there's an entire kind of hierarchy and several layers of abstractions. And even here, I'm telling you, it's close to the reality. Sometimes it's a lot more than that. Okay, and that's something what actually operating systems are very challenging to develop. Okay, and this is why I need a little bit of BO7. So this is also a reason why I'm not going to throw at you Linux and ask you to modify Linux. Not because it's complex. I mean, what it does is complex. It's actually the same concept that we're going to see in Pintos, but the way it's structured, because Linux is highly configurable, highly modular, and so on. It's the code architecture that is actually quite complex. Okay, and it's hard to get into. You will see Pintos has already this kind of abstractions. Okay. So that's it. So here I talk about the first piece, which is the bootstrapping, how the OS starts, and then this system calls, and that's going to be actually your project 0. Okay, that you're going to do. So let's see quickly. Let's try to answer some questions. Okay, somebody says that 6 categories. That's correct. Yeah, I might have added another one. Okay, I'm going to modify that. Thank you. So let's start. The need for so right now what you have done in B58 was running one program. Okay, but in reality you don't run one program at a time, right? I mean, if you look at your computer, it runs maybe hundreds of programs as you speak, right? So here you have multiple programs running. It looks like they are running at the same time. Okay, so we're not going to run a program one after the other. But even if we wanted to do that, how would you do it? So in B58, for example, if you were to run two programs, what you would do is the following: you would put these two programs in memory, and you will start kind of executing A, and then once you're done, you will start executing B. Okay, that's a naive approach. You have a problem here, which is your two programs must be in memory. Okay, so once you're done with A, you should have like B ready to be executed. Okay, well, we're going to see, this is a problem, we're going to solve it a little bit later. But let's look at the execution now. So here, you're going to execute program A, and then after that program B. And, at the end, it's going to take a certain time to execute both. Let's look at what the CPU is doing. Okay, because your CPU is going to execute instructions. But your CPU, most of the time, it's going to do nothing. Why? It's going to start executing instructions. It's going to be doing some kind of mathematical operations and so on, reading stuff from memory and so on and so forth. But at some point, it's going to stop. Why? Because it needs some kind of input, or it needs some kind of something from an input-output. And then you have seen that in your B58 class, right? What you do is the following: you put some kind of an instruction to say, I need something from the device. And then you wait. You wait for the device to do something and to be ready. What does the CPU does during that time? Well, nothing. It waits. Okay, or at least that's what you have done in B58. So it waits for the IO to be ready, and then once it's ready, it resumes the operation here, and then again, again another IO. Okay, and so on and so forth. And you see here, actually, most of the time the CPU is idle. Okay, this is not even representative about how much it's idle. It's idle, 70-80% of the time, even more, depending on the program. And then once it's done, it's going to do the same thing with B, and it's going to be the same kind of story. So what's the thing here? What's the problem? Well, we are wasting CPU here. We have the CPU doing nothing and waiting for the I/O. Usually we call that method polling. Okay, that's what you have done most probably in B58. There is a better way. And maybe you have seen that at the end of B58. What's the better way? Well, you can use another hardware thing, which we call an interrupt. So what's an interrupt? It's the idea of that actually when the CPU is going to kind of ask the device driver to do something, and then rather than waiting for the response, it's going to set up some kind of an interrupt that says, once the data is ready, send me a signal on this interrupt line. And when it happens, the CPU, what's going to do, it's actually going to basically resume what it was doing. So why doing that? How is it different? Because the CPU doesn't need to wait. It doesn't need to check, what's the status of the request it did to the device driver. Instead, what it can do is it can do something else. Like what? Well, execute another program. So here, what you can have is the following actually. You can run two programs concurrently. And this is example, right? So if you do that, first of all, you need to keep the context of execution, right? You need to have the stack and heap values and so on for both programs, because now they're going to run at the same time, okay? But, as long as you have enough memory, it's not going to be a problem, okay? So, we're going to, again, fix that with virtual memory later. And here's what's going to happen actually. So here you are gonna you're gonna do the input, and here you're gonna start processing program A, and at some point you will wait for there will be an input-output, and rather than waiting, you're actually gonna start executing B. The processor is gonna do that. Okay. At some point, it's going to process B, and again, B needs some kind of I/O. So here, the processor is still going to be idle, right? Because there is no other stuff needed. So the processor is just going to wait. Okay, wait for what? Wait for an interrupt. The first one to come is like, okay, this is something telling program A, hey, your IO is ready. Okay, so now you can actually start processing A again, right? And then maybe something later comes and again another interrupt saying, hey, the data that you need for B is there. And so the processor is also going to stop and then resume. And you can run that, every time. So basically here, the idea is like you're going to be greedy, which is if you can execute something, execute it. As soon as you receive an interrupt, you stop what you're doing and you start executing again the other process, right? Let's not talk about priority here, but you try your best to basically stay busy. Now there are still moments where you're going to be idle, right? Because there are still moments where all the programs actually are waiting for some files or for some inputs, and the processor is going to do nothing. But in the end, you see here the time to execute A and B. First of all, taken individually, yes, they may take more time. Okay, individually. So here, the time it takes to execute program A, maybe it's slightly longer. Okay, why? Because at some point maybe A was ready to be executed, but the processor was busy executing B. But overall, if you look at the execution time of both A and B, it's much faster. Okay, so here what we have done is like we have executed those programs concurrently together. Okay, we still have some problems. I mean, actually, the fact that you have concurrency, it generates tons of new problems. Okay, one of them is, well, what if the two programs access the same device, for example? Well, that's something you need to synchronize. Okay, something you need to kind of like the OS needs to go and say, okay, program B, actually you have to wait because A has already requested some kind of IO and you cannot override it. But here, if you look at what I just explained, you might think, okay, there is another problem here, which is the following. What if one process basically takes a lot of time operation and basically never does any IO, or it's stuck on a while loop, actually. So if it does that, it's never going to stop. And if it doesn't stop, maybe, right? So here, this is going to be called the starvation problem, right? So, and here, the problem is more like, how do you give fair CPU time to all of the programs so that they don't starve? Okay, so that's the legitimate problem, and there is a very easy way to fix it. What's the easy way to fix it? Well, you're gonna have a new device, which is a clock. Okay, it's not like an external device; it's something internal to the computer. Clock, and it's gonna set few milliseconds, and it's gonna say send me an interrupt after that many milliseconds. And this interrupt is going to cause actually the CPU to stop executing the current program and switch to another one. Okay, which one? Well, the next one ready to be executed, right? If there is none, okay, I'm going to continue with the same program, but I'm going to give the chance to other programs to be executed. All right, so here it's very kind of a cheap hack, which is like we have this interrupt. This interrupt is going to stop. Okay, so that's how we achieve actually concurrency, and we give kind of a fair time to all the programs. So if I try to summarize here, so if you have multiple program, and here I'm going to use the word program or process. A program can go into many different states, right? So at first, it's created, and maybe as soon as it's created, it's waiting. It's waiting for what? For the processor to execute it. Okay, because maybe the processor is busy executing other process. So usually there are many processes waiting and there is one actually running. But as soon as it's kind of your turn, okay, now the process is actually running. Until what? Until there is an interrupt. Of which nature? Well, it's either an interrupt which is the clock, okay, meaning you're not doing any IO and so on. It's just the CPU is going to stop your execution. It's going to preempt what we call the processor. And it's going to put you again back into a waiting state and execute another one. Okay. Or actually, the process was running, and it needs some kind of an IO. And if it's an IO, it cannot go and be running again, right? So it's going to be blocked, and the processor is going to go and run another one. Okay. It's blocked until what? Until the processor receives an interrupt, and when the processor receives an interrupt, it's not going to kind of directly execute you again, but at least it's going to unblock you, and it's going to put you back into the waiting kind of queue, right, or pool. And then, you can repeat that as many times as you want until, you terminate, basically. Okay? So that in a nutshell, what's happening. So it's great to have this concurrency. I mean, this is what makes our computers doing a lot of things. And from the user perspective, it's a good CPU usage, right? You execute stuff faster overall, right? There is a better use of your microprocessor, okay? It's faster overall, right? Although for executing one program, it's a bit slower because sometimes, the processor is busy executing other stuff. But from the user perspective, from us, for example, using our computer every day, it looks like everything is going in parallel. I can listen to some music while coding, while actually watching a YouTube video at the same time, right? But behind the scenes, it requires a lot of things. It requires to schedule of these programs, okay, to make sure that they don't starve and so on. You have to synchronize them sometimes because they try to access the same resources, okay? And you need to protect them in case something goes wrong, right? We'll define that a bit later. Something I haven't talked about here, but I think that there is only one CPU, okay? And the CPU is running one program at a time, right? It's switching between many processes, but is running one program at a time. What if you have multiple core, which is very the case right now, right? I mean, my Mac has 4 cores. Okay, 4 core means you have 4 different processors, and each of them can run in parallel. Meaning here you can actually execute not only one process at a time, but 4 processes at a time. Okay, so that sounds great, right? You're doing 4 times more job. Well, again, this comes with a lot of logistics, right? When you receive an interrupt, for example, which core do you interrupt? All of them? One of them? And if one of them, which one? And how do you know? And so on. So there's a lot of new problems here that I'm not going to talk about, but we're going to see it during the semester. There are plenty of other problems here that we are going to talk again this semester. Scheduling also is another problem. How do you decide which process to execute? You might say, okay, let's give a fair, share of to all process, but not all processes are equals. Okay. Right now, for example, my streaming process is should have higher priority than a backup. For example, the backup can wait. It doesn't matter if it's slow, but I want my streaming to go fast, right? So maybe actually there's going to be some kind of a priority. Synchronization. Okay, we talk about that. We're going to have to synchronize the access to resources. Communication, how programs can communicate and exchange data and so on. You have done that actually in BO9. This is sockets and signals and so on. And threads. Okay, what are threads? On Unix, at least, they are different than process. It's basically a way to do lightweight concurrency within a same process. So inside the process, you have kind of mini process, if you want, that are running. Okay, why is that useful? Well, we're going to see that actually next week. Okay. So that was kind of like a long introduction about concurrency, but this is just to explain that because we want the operating system to run many programs at the same time, the operating system is going to have a hard job actually to managing all of that. Okay, and that's basically what we're going to do most of the semester. Okay, let me see if there are questions here. What are examples of protection? We're going to talk about it right now. Yes, if B actually takes a long time before calling an interrupt, yes, it would delay the execution of A. Yeah. So that's what I mean. With concurrency, you're not. If you take one program, okay, for sure you're not going to go faster. Okay, you might go a little bit slower actually when you execute in parallel. Concurrently with other programs. You cannot go faster, okay, than if you have only one program. But for sure, overall, if you run multiple programs at the same time, yes, the over execution is going to be faster. That's important. Can you explain the concurrent access to I/O and so on? Well, we are going to see that again week 3. How do you figure out what the core does? Well, that's again another problem, right? How do you allocate basically tasks to execute to cores and so on. That's again another complication, right? Sometimes actually not all cores are working at the same time. Sometimes only 2 of them out of 4 are working because they try to also be kind of energy efficient and so on. So that's going to be interesting. Yeah, we're going to talk about locks and so on with interrupts. We're going to talk about all this stuff in details. Yeah, I don't want to bore you with details. That's going to come. I'm trying to give the big picture. Concurrency is at the OS level, not at the CPU level, right? Yeah, no, it's actually, yeah, it's at the OS level. We're going to look at that. Okay. Usually we say concurrency is at OS level. Parallelism, which is multi-core, is actually at the hardware level. Yeah. Actually, let me show you something interesting, right? Everything I just said, it's there. If I go into, let's look on the Mac, for example. Let's look at these programs running. So you can see, for example, how many processes are executed there in parallel. Well, how many do I have here? It doesn't say the number, but you see it's a lot, okay? It's many of them, I don't even see them as, some kind of a window opened on my desktop, right? All of them get some CPU time, right? Here you can see the CPU time it's actually getting, right? It's showing actually the threads, okay, well, fine. And it tells you actually how many of them are idle, meaning how many of them are actually blocked or waiting and so on and so forth, right? So something interesting here, the first one here, the first process is actually the kernel. It's really the kernel that I was telling you. Here, this is the first process that starts on the system, and this one, which is called process 0, starts all of the others. Okay, and like what you did in BO9, there's a fork, and then another process can fork again, another one, and so on. You get some kind of a tree. And at the top of the tree, at the root of the tree, is actually the kernel, process 0. Something interesting here, if you look at the stats, actually, how often is my CPU idle? Here it says 12% of the time. This is actually very unusual. I will tell you, here it's very busy. Okay, but 20% of the time, the processor does nothing. It's busy because I'm streaming. Okay, I'm recording video, processing video, and so on. But I will tell you, in a normal time, when I just browse the web or code or even watch a video, it's idle 70% of the time. Okay, your processor is idle most of the time. Okay, except if you're doing some intensive stuff like gaming, image processing, video processing, and so on and so forth. Okay. In the past, you could see the core. I don't know if you can see that anymore on Mac. Let's see. You can see the memory. You can see the energy. Well, that's battery and so on. Well, that's maybe not interesting. So in the past, you could see which core was busy and so on when you had the quad core. And it was actually funny because this is how I discovered that not all 4 cores work at the same time. And they do it for energy consumption. They have 2 cores working, and then they let them cool down, and then the 2 others are working, they cool down, and so on, right? So it was very interesting. Okay, so let me resume, because actually we are running out of time. I'm going to try to finish. So, okay. So something else we need is user spaces. What's that? Well, it's kind of like an old problem and for an old constraint. The idea was, in the past, computers were expensive and they were very big, the size of a room. So not every user had a computer, or actually not like now, which one user has many computers, if you count like mobiles and so on. So usually in the past, you had one computer, many users. So OS needs to accommodate that. What's the problem with that? It's perfectly fine, actually. No, it's just running different programs at the same time. So we have just seen that it's possible. But, what if, Alice, for example, has a program that certainly look at what Bob is doing, right? She just do some kind of an operation that looks at Bob's memory, and so she can see Bob's data, right? This is something you don't want to happen, right? You don't want, if you are on a big on a server or something like this, to look at other users' data. Okay. But it goes beyond that, right? You don't want to you don't want Alice to actually stop any programs run by Bob, okay? And imagine Bob is the administrator, right? You don't want her to access any file on the file system, for example. You don't want her to do any input-output, okay? Maybe sometimes you don't want to say, no, you're not allowed to look at the USB, okay? You don't want her to maybe change the system configuration, okay? Or even like reboot the machine, right? So here you understand that what you need to have is some kind of privileges about what you can do on the system and what you cannot do, right? To protect other users. That's the definition of a user space. Basically, what's happening here when you have a user space is like, users have full privilege on their user space. They can do whatever they want, okay? But as soon as they want to actually access to resources in other user space, well, it has to go to the kernel. And the kernel here, what's going to do is going to look at the system call you're trying to do. Everything has to go to a system call. And it's going to try to decide, okay, whether it's allowed or not. How? Well, there will be some kind of a security policy, okay, that is actually highly configurable and so on. But we're going to look at what's allowed, what's not. And you know that actually already, right? With files, for example. Files have an owner, and the owner puts privilege on the file, okay? But actually, it's more than just files. It's everything about what you can do on the computer, right? So here, all systems have that. Windows, Linux, and so on, Mac, they all have this kind of a user space. But I told you, right? It comes from the past where multiple physical users were on the computer, okay? Is it true anymore? I mean, there are very few computers where you have multiple users, okay? Well, for example, you're using MATLAB, maybe, but that's it, right? Most of the time, even if you have your own server, you have your personal computer, your mobile, and so on, you're not sharing computers really, okay? So key, or maybe you share one at home, but less and less, right? So is this paradigm obsolete? Well, no, actually, it's very useful because not all programs are reliable or trustworthy. And having a model of users, okay, it's actually better to provide reliability and security. Okay. And here, it goes beyond the physical user. Actually, let me show you here. Again, my process is here. You see, there's one column here I haven't talked about, which is the user. Okay. And here you can see that, some users are root, but others are actually users, and sometimes, that's me, for example. I'm the only user of the system, but there is some kind of a virtual users and so on to actually run these programs. Why? In case something goes wrong, security issue, or something, the program goes crazy and so on and start corrupting memories or devices and so on. Well, we have actually a way to actually constrain those programs. Okay, so it goes beyond users. So that's why we still have this kind of model. Okay. All right, I'm going to skip the virtual memory here. I just want to have a conclusion. So again, there's going to be virtual memory where you have, well, we're going to go into detail about that. So that's going to be project number 4. One obvious one that you know is a file system. That's going to be project number 5. Okay. What's a file system? Well, you know it, right? It's basically files and directories and so on. Something we take for granted every day we're using our computer, okay? But in reality, this doesn't exist, right? What's there in reality? This. It's a big hardware device with addresses, and you write stuff there, okay? So how do you go from the disk to that? Well, that's going to be actually project 5. And here I can tell you this is a big linked list on steroids. Okay, so that's also something that the operating system does. Okay, so in a nutshell, let me conclude here. What is an operating system? Well, it's a very complex program, as you can tell now, that basically manages the hardware and runs programs. Okay, on top of that, so it creates managed processes, it manages access to the memory, it manages the files, the directories on the file system, enforce protection mechanisms, okay, even though you don't have multiple physical users, but it protects programs from one another, okay. It's better for actually reliability, but also security. And it enables communication between all of this process. All of that This is exactly what we're going to study in the course in details and what we're going to implement. Okay. So quickly here, what you should do for next week. So again, project 0, give me again a couple of days. Couple of days I'm going to finalize, and then you can start working on it. Again, it's not complicated. It's you're gonna be fine. But start reading. Start reading the book, for example. Okay. If you want to have more kind of detail about what's coming in the next lecture. But also start reading about Pintos. Okay, you're going to work on it. Everything you read, you're going to reuse it and so on. You might have to read it multiple times, by the way. Right now, what I recommend you to read is part 0, the introduction, okay, and appendix A, which is how Pintos work. Okay, maybe not everything is going to make sense yet, but that's going to be the first time you're going to read it, and then second time, third time, and so on. And as we progress in the course, it's going to make more and more sense. Okay, so that's it. So let me switch back to the camera here. So first of all, I'm sorry if the quality of the streaming was not good. I'm going to try to, I will try to investigate what went wrong. I might ask you for your opinion in a survey, and hopefully next week it's going to be better. Okay. So if you see something I can clearly improve, please let me know. Let's see. I'm just going to go to quickly the questions here. Okay, yeah, the readings, I'm going to post it on the website. So far, I haven't done that, but yes, you will know what the readings for next week. Okay. Will an email be sent out to modify project 0? No email. I will post something on Piazza. Yes. Okay. So yes, you will have a Piazza message saying when you can start working on it. But again, start reading about it now. Okay. Start reading about Pintos now. Okay. All right. That's it for now. Hopefully you got something from this lecture. Have a good day, and hopefully see you next week with a better quality lecture. Okay. Thank you. Bye.